Welcome. The derivative concept is going to be the topic of this lesson. And first of all, we kind of changed the style. And now, because I was pissed off, and not only pissed off, I was also tired of removing red and watching the green board every time. Believe me, that's really hard. So now, from now on, we're going to record videos and conduct our lessons here in front of the whiteboard. So that's it. All right, the second thing, of course, the derivatives, the derivative concept, derivative. And as I already told you, right, we'll discuss two main problems here, the tangent line problem and the area problem. We kind of introduced the tangent line problem in the first lesson, so now we're going to discuss it properly. And the tangent line problem, that's about derivatives. The area problem, that's about integrals. And you know what? We define both integrals and derivatives using limits. So limits are essential introduction, let's say, to the calculus course. But the real calculus, that's about derivatives and integrals. And of course, but they are both defined by limits, so I can't say something is less important. They're all equally important. All right, so derivatives. And therefore, let's kind of remind the tangent line problem, right? Let me draw a graph using black one. So, xy coordinate system, as usual. Remember, we wanted to find the slope of the curve, right at the point. So we had some curve and want to find the slope at some point. Let's say this point. So the coordinates will be a and f of a. So we want to find the slope at this point. That's the coordinates of this point. Wonderful. And but we didn't know how to do that. But we knew that we can find the slope when we have 2 points, right? And therefore, we sketch the slope, we sketch the secant line. And by the word, the secant line, that's not secant line, that's not about the secant trigonometric function, all right? So that's a different thing. They're not the same, all right? It's not the same secant. So we sketch the secant line, and we said, all right, so this guy, the secant line, what are the coordinates? Yeah, the coordinates will be just x, f of x, generally. So we said that, all right, the slope of the secant line is equal to rise over run, f of x minus f of a over x minus a. So this way we can find the slope of the secant line. So what's the slope of the tangent line? I can't say. That's hard. That's an approximation of the secant line, right? So we can find the tangent line. We can actually find the tangent line right now, but we can approximate it using the secant line. So that's what we said. All right, so we can approximate it, but can we somehow make the approximation better? Right, yes, we can. And we do that by taking this point closer, yeah, and getting our point closer and closer to the point A. So by doing this, we're going to get a better and better approximation every time. And if we get this point, get really close to this point, then the slope of the secant line will be really close to the slope of the tangent line. So that's what we already discussed. And therefore, that's by the word rise over run, yeah, or also delta y over delta x. And we discussed that, all right, so if we take the limit of this expression, right, f of x minus f of a over x minus a, so if we take the limit here, as x approaches a, yeah, gets really close to a, then we'll get the slope of the tangent line. And I can even say, in fact, that's a definition of the slope of the tangent line. So this way we define the slope of the tangent line to a curve at a point A. So if we have a curve, first of all, of course, if the function is defined at point A, right, and we have a graph f of a, right, so the function is defined at some point A, then we can find the slope of the curve or the slope of the tangent line to a curve, they're the same, at point A by taking this limit, evaluating this limit. So this is the definition, in fact, of the tangent line to a curve at a point A. So this way we define the tangent line. And by the word, of course, we can, so we call this thing difference quotient. We call it difference quotient. And in fact, yeah, if we remove the limit, what does it mean? I also said you that that's just an average rate of change of your function, the slope of the secant line. That's the average rate of change of your function, average rate of change. So this way, the slope of the tangent line, that's also the instantaneous rate of change, right? It shows you how fast your function changes at an instant, at point A, at some instant. So that's about the idea behind the slopes of the secant line and the tangent line. All right, so this way we can define the slope of the tangent line. Also, sometimes you can see different notations, right? Instead of saying that this is just some x, f of x, sometimes someone says that that's the coordinates are a plus h, for example, then the function is a plus f. So the function, the y coordinate is f of a plus h, right? And then, so the difference quotient will be f of x plus h minus, oh, not x, a plus h minus f of a, right, over a plus h minus a, which is h. And here we'll have, as usual, limit. But here they will want h to approach 0. So this is basically the same. They are similar, right? They're both definitions, but the difference is only in notation. And in fact, you can use any of them, of course, as you wish. So you can choose this definition, you can choose these. They both define the slope of the tangent line. So this way we can define the tangent line to a curve at a point. Wonderful. That's also slope of the tangent line. Good. In fact, again, we defined that, right? So that's a definition, that's a concept, the slope of the tangent line. Good. And what's funny, the same expression, the same limit is also used in order to introduce the derivatives concept, right? In order to define the derivatives. So let's actually remove this from the board. All right, before that, let's actually practice a bit and let's solve an example here, solve a problem. So we have a graph, so the function is x squared plus 1. Wonderful, we want to find the slope of the tangent line to this curve at some point. Let's choose the point. Let's say the point is, I don't know, 1. Let it be 1. So we want to find the slope of the tangent line to this point. Let's draw it with green. So it's our tangent line. And we'll find the slope of this tangent line. Let's do that. So, how do we do this? We say, all right, we need to evaluate the limit as x approaches the point, and the point is minus 1. X approaches minus 1. And of course, the first question, does limit exist? Of course, yes, because both from the right and from the left we approach the same value, and we already see that of course there is some limit, right? So it's fine, and the function is continuous at that point. All right, so the limit exists for 100%. So what's the limit as x approaches minus 1? And now we just have to write down the slope, right? The formula was that there is f of x minus f of a, right? So what's the point here? That's minus 1. F of minus 1 over x minus a. And here it's minus negative 1, so that's plus 1. Right? So we want to evaluate this limit and then we'll obtain the final answer. That's it. Let's also rewrite it, yeah. Substituting x squared plus 1, x squared plus 1 minus, and what's the function at point minus 1? F of minus 1, that's going to be minus 1 squared plus 1. What's that? That's just 2. Correct. So that's just 2 over x plus 1. Yep. And so, what's that? That will be limit as x approaches minus 1, x squared plus what? Minus 1 over x plus 1. And now we just have to factor so we get x minus 1, x plus 1 divided by x plus 1. And therefore, the final answer will be the limit of x minus 1 as x approaches minus 1. So that will be minus 2. So the slope is negative 2. Is it real? Yeah, kinda. It's kinda true. Just look at the slope, of course it should be negative. And we see, yeah. So it's kinda true. The answer is minus 2. This is the slope of the tangent line to this graph at point minus 1. And basically, the hardest part was just to construct the limit, right? Then everything is very easy. That's just evaluating super simple limit. And that's it. All right, now derivatives. All right, so I've decided to keep the picture for a while. Maybe we'll need it. So we discussed that we can find the slope of the tangent line as the limit of the difference quotient, right? F of x minus f of a over x minus a as x approaches a. So this way we can find the slope of the tangent line at point A. Right, this is the slope of the tangent line. And there's also a different name for that expression. We also call that the derivative of function f of x at point A. And we denote that f prime of a. So that just means the derivative of function f of x at point A. Alright, so we also said a few seconds ago, right? So this is the limit of the difference quotient. And difference quotient can be written in a couple of ways, in fact. So we can also write it down this way. We can say that, what's that? This is change in y, this is change in x. Change in y. We can say that this is f of a plus h minus f of a. If h is change in x. H is just change in x. So you had some point, or from here it was f of, again, that was a f of a, right? That's the coordinates of this point. And we take some secant line, and the coordinates of the secant line are a plus h, so h is the change in x, and then the value of our function at that point will be f of a plus h. F of a plus h, right? So that's clear. So in fact, h is changing x, and this is changing y. And then what do we need? We want the change in x to shrink, yeah? So we want to let h approach 0. This is the same thing as I already mentioned that. So we can also say that this is definition of derivative as well as this. They're both the definitions of derivatives at point A. So we can find the derivative of function f of x at point A this way or this way. But the beauty of this, let's say, method, right, this variant of the different quotient is that now imagine I want to define the derivative as a function, right? So this is the derivative at some point A. But what if I want to define it as a function, right? I want to get just universal, general function, then substitute any number a, and I will get the derivative at point A. So what if that? What happens here? So from these different quotient, that's pretty easy. We see that, yeah, we just have to replace a by x. So we put here any x, any point, x will be the variable, and then yeah, this way we can define the derivative of a function f of x. So that's pretty easy. If we say that, we say that the derivative of function f of x is the limit of f of x plus h minus f of x over h as h approaches 0. So this is going to be f prime of x. So this is the definition of the derivative of function f of x. The difference only in this, right? A and x. So we just replaced a by x. And now this is the variable. Now the point is variable. Now we can choose any point. And if we want to obtain this, right, derivative f prime of a, then sure, we just take our function and substitute a. If you substitute a, we're going to get this limit. So it works. This is the definition of the derivative of the function f of x. This way we can define the derivative. Beautiful. And of course, it works for all x's where limit exists, right? So limit should exist, of course. So it works only for x's of function where limit exists. And of course, function should be defined. Okay, not always. We already know that not always. All right, one more time. If I have a function f of x, then the derivative function f of x is given by this expression, right? The limit of the difference quotient as difference in change, the change in x approaches 0, right? As h approaches 0. So this way we can find the derivative, of course, provided the limit exists. And for every x where our limit exists, then the f prime of x is going to be the function of x, of course. Wonderful. Of course, sometimes in different books, you will see that instead of h, they use delta x, k, p, l, whatsoever. I don't really care. They can choose any symbol, any letter. The main point is that that's going to be changed in x anyway. Change in x, and change in x should approach 0, it should shrink to 0. So this is the main condition. What letter they choose, that's not super important. All right, I guess that's clear. Wonderful. A few moments about notations, right? So sometimes, especially if we say that y equals f of x, right? Instead of f prime of x, we're going to use dy dx. This just means the same thing. Again, that's a derivative. But we're going to read it derivative of y with respect to x. Derivative of y with respect to x. Also, instead of y, we can write down f of x, right? Then it's going to be df of x dx, right? Again, that's just the derivative of f of x with respect to dx, well, with respect to x, right? Of course, in short, we'll just read dx, dy dx. And yeah, we can use f prime of x. And of course, if y equals f of x, we can also say that y prime. I hope that's all, right? But I don't think we'll use any other notations. That's just how we'll write it down. Now, let's solve some problem. Oh, no, one more moment. Of course, the process of finding the derivative is called differentiation, right? And the function is called differentiable at some point, at point x, right? If this limit exists there, that's it. And the function is differentiable on some interval ab, right? If the limit exists there at every point, at any point. So the function f of x is differentiable if this limit exists, if derivative exists, right? So, and also it's differentiable on an interval, an open interval ab, closed, open, if the limit exists at every point inside, right? So, and that's all now. So in the process of seeking f prime of x is called differentiation. Now we can solve the problem. All right, so here's the problem. We'll start with this function. F of x equals x cubed plus 2x. Let's find the derivative of this function. Let's find f prime of x. F prime of x. This is what we want to find. And we just have to recall the definition. So in fact, we want to evaluate this limit. So the limit of the difference quotient. Fx plus h minus f of x over, let's write it, h, right? Difference in x as h approaches 0. Wonderful. Yeah, sometimes I'll write f this way, sometimes I'll write this way, I don't know, yeah. It's kind of weird. That's the same letter, okay. Good, so I want to take this integral. Now, let's just substitute our function, right? Everything is very simple. What is f of x plus h? You just have to look at the function, and instead of every place where you have x, now you just have to take that place and put there x plus h, right? Instead of x, you have to put x plus h now. Instead of x here, you have to put x plus h now. So that's all. This is how you obtain f of x plus h. So replace x with x plus h everywhere. So that will be x plus h cubed, right? Instead of just x cubed, we are going to get x plus h cubed plus 2x. Instead of 2x, you are going to get plus 2x plus h. So as I told you, just replace x with x plus h minus f of x, which is x cubed minus 2x, right? So we need negative f of x, in fact. So it's just minus everywhere. Wonderful. And we divide it all by h. And why can't we now take the limit right now? Because of course we have 0 here, so it sucks. We have to somehow now simplify, do some algebra, all that stuff, in order to somehow factor the h and then cancel out h. And if it doesn't work out, then we're cooked. We can't evaluate the integral for 100%, not integral in limit. Because so our main goal is to make sure these two guys disappear here, and all the terms that doesn't have any h nearby. So of course we also have limit here. It's not just equal. Limit as h approaches 0. Wonderful. And yeah, let's now simplify this, expand these, everything. And let's then try to factor. And I hope it will work out. So this is equal to x cubed plus 3x squared h plus 3xh squared plus h cubed. If you don't remember the formula, you can, even if you don't remember any formulas, then you just multiply x plus h by x plus h plus by x plus h, and then you're going to obtain the same answer, but that's just a bit longer. Yeah, and if you remember at least quadratic formula, at least something, right, then you're going to get, you'll do less steps, but anyway, in the end, eventually, you'll get the same expression. Wonderful, but I remember the formula, so I'm not going to do that. Then, plus 2x plus 2h and minus x cubed and minus 2x. Now we have to pray and really beg the universe that x cubed and 2x is gonna disappear here. So x cubed, good, first one cancels out. 2x, yes, there is also plus 2x and negative 2x. Wonderful, whoa. Now yeah, of course h in the denominator. So wonderful, we will able to look at all the terms we are left with. They all have h somewhere. So it means we will be able to factor h and then cancel out this thing. All right, so limit of 3x squared h plus 3x h squared plus h cubed and plus 2h over h. So we want to now factor and we will be able to obtain the final answer. So the final, of course I forgot, h approaches 0. So that will be 3x squared plus 3xh plus h squared plus 2. Okay. And all over h. So h cancels out, job is done. Now we just have to substitute 0 into our expression. So that will be 0, 0, 3. So this is going to be 0, this is going to be 0. We'll be left with 3x squared plus 2. So the final answer and the derivative f prime of x, the derivative function of x is 3x squared plus 2. So this is the answer. Or also I'll try to use different notations now. Wonderful. So what did you find? We find this by the word, yeah, maybe by coincidence, but that's the same thing. Yeah, we found the derivative, but we also found the slope of the tangent line, right? We found the slope of the tangent line to this curve at any point, right? We can take any point and we'll obtain the slope at some point. So we found the slope of the tangent line as a function. That's even better. So just remember, every time when you find the derivative, you also find the slope of the tangent line, okay? So we found the slope of the tangent line and we found the derivative, and they are the same. Next example. All right, next example. F of x now equals the square root of x. And we want to find the derivative, of course. We want to find f prime of x. And we also want to find the slope of the tangent line at this point. Wonderful, so let's start. Let's start with derivative, of course. So f prime of x is equal to the limit of the difference quotient as h approaches 0. Good. So let's write it down in terms of our function, right? So that will be, again, what will be f of x plus h? We just have to replace x with x plus h. So that will be the square root of x plus h minus the function of x, that's just square root of x, over h. And I also, by the word, forgot about the limit. Good. So we have a radical in the denominator, so for 100%, and of course we already discussed that I can't just evaluate the limit right now because I have to cancel out h. So it all means what it means. We're gonna multiply by conjugate and conjugate again 2 times, right? So we have a radical here. I wanna simplify the expression, so we have to multiply conjugate. And here it means to multiply by x plus h squared plus square root of x, not squared, the square root of x plus h plus square root of x, and the same thing here. Because we can always multiply by 1, right? Nothing really changes. So let's see what happens next. Here we will get x plus h minus x all over h square root of x plus h plus square root of x. Oh yeah, and again, our main goal here is to cancel out h somehow. It's our main goal, and if it doesn't work, if we can't simplify h, then something is wrong because yeah, you won't be able to finish the problem. So the limit, and we see that everything will be fine here because x and x we are going to simplify, cancel out. So we'll be left with only h over h and this, so we'll cancel out h2. So that's because it's x minus x 0. So in fact we have here h only. So that will be the limit of 1 divided by square root of x plus h plus square root of x. And if we substitute 0 now, we'll get that the final answer is, and the derivative is just 2 square root of x. 1 over 2 square root of x. So this is the final answer. This is our f prime of x. Wonderful. And the second part of the problem, we want to find the tangent line problem at these, the slope of the tangent line at this point. And of course, we already found the slope of the tangent line as a function. So the derivative, that's also the slope of the tangent line. Now, all we have to do is just to substitute the point, right? Instead of x, we have to substitute 4. So in fact, the slope of the tangent line at this point, that will be f of 4, right? F prime of 4. Just have to substitute 4, and then we'll see that that is equal to 1 over 2 the square root of 4. So that's 2. So it's just 1/4. Okay. Let's keep it 1/4. So this is the final answer. Very easy, right? We found the derivative, and we also know the derivative is tangent line, the slope of the tangent line. Then if they want us to find the slope of the tangent line at this point, then that's pretty easy. We just have to substitute the coordinates, right? The x coordinates, and then we'll get the slope of the tangent line. So that's 1/4. All right, so we follow the exam and course book description. Therefore, we have to at least talk a bit about the estimating derivatives. But I don't think that's something genuinely new, because we already discussed how to estimate limits. And what's the derivative? That's the limit, in fact. That's just the limit of difference quotient. So you have a function f of x, and instead of just estimating the limit of f of x, you are estimating the difference quotient of f of x, and that's it. So here, your limit is, let's actually use this type of difference quotient, right? An alternative f of x minus f of a, x minus a. It's just more convenient when it comes to estimating. So this is the definition of a derivative, right? So that's also a unit. That's also a limit, right? Nothing changes. How did we... First of all, if you talk about the graphical estimation, then it's very easy. We already discussed that. How do we estimate the slope of the tangent line? We just estimate it by the slope of the secant line. It's super easy. Yeah, that's actually how we defined, how we came to the tangent line, by the approximation. So if you talk about graphical approximation, I guess it's clear and no questions. That's just how can you approximate the slope of the tangent line? By the slope of the secant line, and that's it. The graphical approximation, that's also not hard, because we just have to construct the table where we have x. So first, imagine I want you to find, and you can't analytically find the limit, right? Evaluate the limit in order to find the function. And I want you to find f prime at point 2. Then point 2 somewhere here. So 2 is here. Then we take, and instead of f of x here, we'll have g of x. G of x, I will just call the difference quotient this way. So that's just f of x minus f of a, x minus a. So now you substitute, right? different points, of course nearby, very close to 2. You take points close from the right, 2.01, 9.99, 2.1, you understand, 1.9, and then you substitute it into our g of x. A here is 2, right? We want to find f prime 2, and that's it. And this way you will be able to estimate the derivative. So nothing is really new, the same thing. The only difference is that instead of f of x, now you will have g of x. That's just difference quotient. Now we'll estimate difference quotient. That's the only difference. Alright, one more small thing to note. Of course, that's not really important, especially for our exam, right? For AP Calculus exam here, it's not really important. But however, yeah, I gotta say that even your calculators, yeah, and most of the machines, they approximate not by taking this type of difference quotient. We can also find the difference quotient, define the difference quotient this way. We can say that this is f of x plus h minus f of x minus h over 2h. Again, we don't use this type of difference quotient in order to define the derivative, right? We don't use that. And we won't really use it, but in order to approximate the derivative, it just gives more precise answer. And that's all. So in fact, that's just good for approximating. This way, it's better to approximate the derivative at some point. So you take a point, for example, 2 here, right? And imagine you want to approximate f prime of 2, right? You want to approximate your derivative at point 2. And you just have to take, as usual, you take h really small, right? What's h? That's difference in x. You take h, I don't know, super small, 0.01, 0.001. You understand? You take just small h's and that's it. And this way actually it just gives you more precise answer. But all the things we discussed before, they will also lead you to the right correct approximation. But this just gives you more precise one, and that's it. So, but basically, if you don't really, that's just a kind of just one more thing to know, and that's it. It's not really important information here. All right, and the last thing for today is going to be that differentiability and continuity, right? And the fact that what's funny, and that's not even super funny, that's just a fact. If a function f of x is differentiable at x at some point, right? If function f of x is differentiable at point c, let's say, then it's also continuous. So differentiability implies continuity. That's the kind of theorem. So if our function f of x is differentiable here at point c, then f of x is also continuous at point c, differentiable at this point. So this is the theorem, and we can really prove it, I can even say easily. So what means, we just have to look at this limit, right? We say, okay, let's look at the limit f of x minus f of c as x approaches c. We want to look at this limit. Imagine, so we say that the function is differentiable. Wonderful. All right, now let's try to simplify the expression. So what's f of x? So what's that? And I suggest to multiply and divide by x minus c, for example. Let's even take not c, let's take a. Right, we're already got used to a. So at point a. Now, if we multiply now and divide by x minus a, and we multiply, so this thing stays the same, but now we multiply and divide by x minus a. And this is also equal to the limit of x of f of x minus f of a over x minus a, right? Multiplied by the limit of x minus a. We can split it up this way, of course. Nothing changes. We still take the limits. So we didn't break the rules. So it's fine. And look at that. We said that it's differentiable at point A. What's that? This is f prime of a, right? Okay, then, and what's here? That's just a minus a, so 0. So in fact, eventually we get f prime of a multiplied by 0. And that's 0. So it means this limit is equal to 0. And look at the limit. So it just basically means that f of x is equal to the limit of f of x as x approaches a is equal to f of a. So we proved the theorem, and it means that function f of x is continuous at this point. Because, of course, it also means that the limit exists and the function is defined. Everything is already, so all this theorem already contains that properties, let's say. Wonderful. So differentiability implies continuity. Good, but it doesn't work in the opposite direction. Yeah, so continuity does not 100% mean that differentiability exists. That it doesn't mean that your function is differentiable at point A. Right? If your function is continuous at point A, it doesn't really guarantee that your function also is differentiable at point A. And let's give an example where we'll show it. Alright, differentiability implies continuity. Wonderful. We said that, so if your function f of x is differentiable, it also means that it's continuous at some point. Right? If it's differentiable at some point, it also means that it's continuous at that point. Wonderful. However, it doesn't work in the opposite direction, not always. So if your function is continuous, it's not guaranteed that your function is also differentiable at that point. And here's the example that will show you that. Imagine we have a function f of x, which is the absolute value of x minus 2, right? So, and let's look at point 2. And the function is continuous. Why? First, because the function is defined, right? So at point 2, the function is equal to 0, right? So we put 2, we're going to get 0. Second, we approach the same value from the left and from the right. So from left hand limit is equal to right hand limit and is equal to 0. If we approach the same value from the left and from the right, that's 0. So the limit exists, and that's equal to the value of our function at point 2. So the function is continuous, that's proved. Our function is continuous at point 2. Wonderful. Now let's look at the derivative here. And I decided to write it down in this notation. Right, that's also a definition of the derivative, just an alternative. So f of x minus f of a over x minus a. So this is f prime of a. And here, in our case, in our situation, that will be f prime of 2, and that's the limit as x approaches 2 of f of x minus f of 2 over x minus 2. And so we want to show, because that's the example to show you that continuity not always means differentiability. I want to show you that this limit does not exist. How can we show that it exists or doesn't exist? So what do? We have to look at the left hand and right hand limits, right? And if one side limits are not equal, then it means that the limit doesn't exist, of course. So let's look at that. And therefore I chose this notation, yeah, because that's just easier using this definition of derivative. Look at the left hand limit and the right hand limit, so it's just easier. Let's do that. So that will be what? That will be, so from the left we approach what's here, f of x minus f of 2. So that will be the absolute value of x minus 2 minus 0, right? Over x minus 2. And of course, we can remove the vertical bars here because we'll approach 2. So it means that's just equal to 1. I guess that's clear. Now, what happens if we approach the value from the right? Oh, it's not equal to 1, right? So, no, it's equal to 1. Everything's fine. Wonderful. So we know that this is, oh no, we approach from the left, right? So x is less than 2 for 100%. So it means that this is negative, right? So we need a minus here. So it means that this is equal to minus x, let's write it down this way, minus 2. Negative x minus 2 over x minus 2 as x approaches 2 from the left. And that just means that the limit is equal to minus 1. And now if you look at the limit from the right, then I guess you already see what will be the crucial moment, right? That's just about, that will be the absolute value. That here, of course, that will be just, so we approach from the right. X is greater than 2 for 100%. So we can remove the vertical bars and we don't even need any signs. So that will be just, so it will be this, right? And then we cancel out and we get, right? And that will be 1. So the right hand limit and left hand limit are not equal. So we approach different values from the right and from the left. It means the function, the limit doesn't exist, and if the limit doesn't exist, it means just basically that the function is not differentiable at that point. So we proved that. Alright, that was all for today. Of course, we're not going to find derivatives by evaluating limits every time. It takes too much time, we need too much effort. So we'll be able to develop a new tool next lesson in order to obtain these derivatives in a much easier way. So see you soon. Happy studying. Smash AP.